Okay, so we take the y equals 3x, place it in for y in the second equation. Then go ahead and solve for x. X plus 3x is 4x. 4x equals negative 32. Divide by 4. We get x equals negative 8. Now take the equation that was already solved for y and plug in negative 8 for x. And so we have y equals negative 24. This is a good example of one where you wouldn't have wanted to graph this to find the cost at negative 8, negative 24. Negative 24 is quite a ways. Yeah. So the solution is just negative 8, comma, negative 24. That's where they cross. You can box it. I'm going to get you started in the second one, and then we will circulate and kind of see how you're doing on it. I want you to find the solution to this system of equations using substitution. This time we're going to take 2x plus 7 and put it in for y in the second equation. Or another way to think about this is you could set the two equations equal to each other because they both equal y. So go ahead and solve that for x. Go and plug it in and find y. Here, I'd like to see it. You have x. Wait. I can show. I'll show you with this.
Boy.
All right, so you got how do you start with it?
Wait, so negative 2?
You got it.
So negative 1x? Oh.
Negative x equals 8. Yep. X equals 8. And what is x equal? Yep. And if x equals negative 8, right, go plug it in and find y.
Find the good old y.
You did it? So you're going to set these two equal to each other.
Yeah,
So, like 2x plus 7 is y. Yeah, then you get to find y. Y equals negative 8. That's a good start. Now solve.
You can
Get it? 7. You did it? Yeah, so now you put the negative in and then after that,
Negative 6. Negative 6. I was just wondering what negative 6 is. I can't. Yeah. What do you mean? These policies inside your Are you doing?
Y equals.
Yes.
While I was looking at like, so what this is doing is we have traded like T. And I was like,
Yeah. Did it?
I love these terms.
Right, so let's take it from here. Take some times 7 a normal equation solving. And then now subtract.
Want to get x by itself.
Then you have x equals. So that's your x value for your cross. Yeah, either one. All right, so let's just make sure we got negative 8, negative 9. We should have gotten all of that.
That's horrible. Oh,
Negative 1x.
that's horrible. I was
Right,
just
Jen.
oh,
You're making it a long way process.
Jen, brother. Yeah, that's good.
You have
so it's pretty easy.
yeah. So I don't think 15. A lot of
And now you're still going. I did the same.
See, there's a
Yeah.
and I actually had a video to
That's it.
and yeah, but there, it's just give an X. So it's right here. You have to plug in and make it so we can do the top three.
What changes?
Wait, are we supposed to continue on?
Yeah, let's go to problem 2 here. So we're going to take it to a little harder level here, a little more difficult.
Just gotta see this side.
If you notice, each of these, neither one is solved for y. That's the difference between this one and the previous example. So this is a little harder. A lot of students, once they have learned the elimination method, if you remember that method, would probably choose that method for this problem. But it can be done with substitution. I'll show you how to do it. Okay? Don't write anything down yet. I'm going to take this first equation, just pretend I'm going into this blind. I know I need to get it solved for either y or for x. I'm going to go ahead and try and solve the first equation for y. And then I'll talk about why I don't write this down. Because there's, I think, an easier, between these two, there's probably one that's a little easier to plug into the other. And you don't really know that until you put it in slope-intercept form. So if I were to take, say, 3y plus 4x equals 12. Once again, do not write this down yet. Just wait. I would subtract 4x from each side. It's that two-step process we've been working on to get it in slope-intercept form. And then I would divide each term by 3. And I get something in slope-intercept form. But if you'll notice, I do have a fractional slope out here. So if I were to take this and plug it in for y in the second equation, it's going to be a little more work than it will be if I take the second equation and solve it for y and plug it into the first. So it's one of those deals where if you can kind of look at it and do a little bit of the algebra in your head, you might be able to decide which equation would be easier to solve for y than the other. Okay. But if I were to take and put that in, it's going to be a little messier than if I take, and now you can write this down to show you here. If I take this second equation right here, and I add 2x to each side, so go ahead and do this with me now. So we've got 2y equals 2x minus 6. Just because of the fact that each of these numbers is divisible by 2, you're going to end up with a slope that's not a fraction, and so it'll make a little easier substitution process here. So divide by 2, divide by 2, divide by 2. Y equals, I'm going to write this in red here, x minus 3. So I've got y equals x minus 3. That's a little easier than the negative 4/3 x plus whatever I have there. And so it's your choice. You can solve for either x or for y, and you can solve either equation for that variable. It's your choice. You just kind of want to think it through maybe first before you do it. So y equals x minus 3. Now I'm going to take this x minus 3 and I'm going to put it in for y in that first equation. It looks like this. It's 3 times x minus 3 plus 4x equals 12. So I'm substituting in x minus 3 to the first equation for y. Now I have an equation with just x's in it, and I can go ahead and solve that. I got to distribute. So this takes us back to, our first skill of the year is solving a multi-step, one variable linear equation. We distribute first. Remember what's next on this? Yeah, combine those common terms just on one side of the equation. So do that first. 4x and 3x is 7x. Okay, just careful with the signs. There's a plus on the 4x and a positive 3x. So the negative goes with the 9. And now it's just a two-stepper from here. It's not real difficult. Add 9 to each side. So I've got 7x equals 21. Divide by 7. And x equals 3. So if I were to write, my solution down, I've got 3 comma something. How do I get the y coordinate that goes with this 3? You do, and there's definitely I've already solved this for y right here. So if you look at this guy right here, this is the one to plug it into. I mean, you can plug it into the originals if you wanted, up here or here, but that's a lot more work. If I can plug in 3 right here, I have y equals 3 minus 3, and 3 minus 3 is 0. So the y coordinate here is 0. So it crosses at 3 comma 0. Okay, before I have you try the now you try problem, your classwork sample problem here, let's talk about it just briefly. As you look at those two equations, which one do you think is easier to solve for which variable? Like, is it easier to solve for y or for x, do you think? And you could, it's not bad to solve for y. I mean, you could do it. In which equation would you solve for y? First or the second? And when I'm looking at this, in the first equation, if I subtract 5x over, I'm eventually going to divide by 6. I'm going to have a negative 5/6 x. I don't really want to substitute that in. This one over here, I could solve for y. I'd subtract x over, divide by 3. I'd have a negative 1/3 x. So either one, solving for y, I'm going to end up with a fractional slope. What about if I solve for x in the second one? Could I just solve for x and then substitute that into the first one? What would that look like? I know we haven't solved for x yet. We've been putting it in y equals form every time, right? But it's okay to solve for x in this substitution process. As a matter of fact, sometimes that's a better choice. So right here, if I subtract 3y from each side, I get x equals negative 3y minus 2. And I think that's probably the easiest choice here for solving for a variable, because the x is already by itself. Okay. So when you see two equations, you see a y or an x by itself, where you just have to do one step to solve. That's the one I would solve. So here we have 6y. So we're taking this equation. We have 6y plus 5 times x equals 8. And in this case, x is your negative 3y minus 2. So this time I'm going to solve for y first, and then go back and plug in the y to get my x. So go ahead and try that. Here, you could try that and come look at it. should do this. Yeah, but negative 3 minus 2. You don't want to put it back to this, because then they will cancel out. That's correct for y. Find the simplest version. There's x's on this cell. X equals negative 2 minus 2 is equal to negative 2. So, you got it. Yeah. That's correct. Didn't you know to do negative 2? That's right.
So you want to look, should you play it?
It is. Why is negative 2? It's good to put the negative 2 in here and solve for x.
So y is correct, and that is
Right. X equals y. Negative 3 times negative 2 minus 2. So it's negative 3 times negative 2 is all that. And x equals whatever. Yeah, negative 3 times negative 2 is
Oh.
6. It's 6 minus 2.
Oh,
so where do you plug in that negative 2?
Alright, so we have
Honestly, don't plug it
Alright, so we should get on this one. I know the y, let's see, it was 4, negative 2, right? We should have gotten a 4, negative 2. Alright. So we're going to go on to creating an equation first, and then it'll be of this form. So this is a word problem here. It says a snack bar sells 2 sizes of snack packs. A large is $5 and a small is $3. In one day, the snack bar sold 60 snack packs for a total of $220. So if I let x equal the large ones and y equal the small, I have what's called a total equation that represents the total number of snack packs or tickets or whatever. But this is the total number. No dollar amounts involved in it. Okay, nothing multiplied by the x or the y. It's just the straight total, what I call the total equation. And then there's going to be a cost equation or some kind of equation in which we apply some multiples of x and y. So if it costs $5 for a large, we'd have 5x plus $3 for a small, 3y, would equal 220. And so we end up with 2 equations, look like that. And we're kind of back where we were on problem 2. Right? I have 2 equations, 2 unknowns. I've got to decide on which equation to solve for x or for y. It's your choice. So looking at this one, it's probably easier to solve this first equation, and I might as well solve it for y. Like it doesn't make any difference. But this first equation, I'm just going to rewrite it. X plus y equals 60. And I'm going to subtract x from each side. So I have y equals 60 minus x. And that's going to be my substitution expression. So I'm going to put 60 minus x in for y in the second equation. So this one right here, let's just circle it. I'm going to replace y with 60 minus x. So it would look like this. I'll write it over here so I have the room. 5x plus 3, and then in parentheses, 60 minus x equals 220. And then I can solve this word problem. Notice that they only ask for small snack packs. So if I were really thinking ahead, I would have solved for x in terms of, let's see, yeah, x in terms of y, and then I would have been done when I found y, because the y is the small snack packs. But that's okay. We'll find the number of large ones here. Do our algebra, distribute, then combine like terms. 5x minus 3x is 2x plus 180 equals 220. And then if I subtract 180 from each side, I get 2x equals 40. So when I solve for x by dividing by 2 on each side, I found the number of large snack packs. So this is the number of large ones. And what they're asking for in the problem is how many small snack packs did I sell. So they're asking for smalls. That's represented by y. I've got this expression for y right here. Just do 60 minus 20. And so y equals 40. That's small snack packs. That's it. So the big thing here is just being able to write the equation. I think once you've written it, you'll be fine with solving it. It's very similar to problem number 2. So let's on the now you try. Let's just see if we can write it. Why don't you take just a moment to read it and see if we can just write the equation. We're not going to solve it. Okay, we've done the solving of these types of problems. Let's see if we could write an equation. It says you pay $22 to rent 6 video games. Store charges $4 for new games and $2 for older games. Let's agree to call the new games the x, the older games the y. What's one equation you would have here? Give me one. 2. Yeah.
4x plus 2y equals 22.
Yep. So 4x plus 2y equals 22. That's what I would call, the cost equation. What about the total equation? How many total video games do we end up getting? Not a big number, but looks like 6, yeah. And so, we would have some combination of new games and old games. I don't know what the combination is, but we have x plus y equals 6. There could be 4 new games and 2 old ones, or 5 new games, 1 old one, or 3 and 3, or 2. There's different combinations, and that's it. So once you have that, then you could solve it, and there's just one unique solution with those 2 equations, because once I bring the cost into it, that gives it one unique solution. You could actually guess and check your way there too. I mean, you could keep going, but probably the algebra, doing the substitution, is more efficient than guessing and checking in most cases. One more thing to address here, and that is, do all systems have a solution? Well, when we were graphing, and you had parallel lines, remember the parallel lines case? There's no solution. And when you were graphing and you went and solved for y, and you noticed both equations were the same equation, they had infinite dimensions. So I just want to show you what that looks like when you're doing substitution. So if I take this x is equal to negative 2y plus 4, we got 3.5 times negative 2y plus 4 plus 7y equals 14. So I'm just plugging in negative 2y plus 4 for x. If I do the algebra here, distribute, I get negative 7y plus 14 plus 7y equals 14. Something interesting happens here. My variable completely disappears. It's negative 7y plus 7y is equal to 0. I get this statement, 14 equals 14, which is true. It's true. 14 does equal 14. What's the interpretation, do you think, of this? Like, which case would this fall into, the infinitely many or the no solution case? Okay, both are good. It's got to be one of those, yeah, but it's when it doesn't matter what y was, it's the infinitely many case. So when you get a true statement, it's the infinitely many. And in this one, if I take the 3x minus 11 and plug it in for y, it looks like this. We're going to get our other case. The 3x's cancel out. We get negative 11 equals negative 13, which is false. When you get a false statement, that is your no solution case. So in your homework, I just want you to look at your packet or your green sheet. Do the homework is just as it's stated. There are 7 problems. There are 2 of them that do fall into this special case where there's no solution. It's kind of nice when they do because you know pretty early on. It's actually less work than the one solution cases. Can you tell looking at this one which one this might be? Put the x equals 6 minus 3y in there. 5, 6 minus 3y plus 15y equals 30. 30 minus 15y plus 15y equals 30. So can you tell at this point? 30 equals 30 is the infinitely many case. So you might want in your summary just note infinitely many, no solution. You know what's happening. If you get a true statement, it's infinitely many. If you get a false statement, it's no solution. You might want to add that to your summary. So please write a summary. And don't forget to do the homework.